Right. Good morning, everyone. Okay, the next topic that we'll take up is enolate ions. Okay, so I'm going to share my screen. Okay, we are on schedule, and so for Friday class, make sure that you have something to write with. We're going to be doing some review. And then after we come back Monday and Wednesday, we'll have review practice as well. Friday will be the chapter exam, and then the following week will be finals. Okay, I'm supposed to give the final exam on the designated day. I can have a larger window than what is on the schedule, time window than what is on the schedule. Okay, give me just a minute to open this up. Okay, there we go. And okay, I'll start off by sharing my screen. Right, today we look at enolate anions. This is actually an important reaction not only in synthetic chemistry, but also in biochemistry. Okay, I'll wait just a minute for everyone to enter. Okay, first we start out by defining what is meant by the alpha carbon, alpha to a carbonyl, and that is the carbon right next to it. And on that carbon, you may have alpha hydrogens. Alpha hydrogens of aldehydes, ketones, and esters are considerably more acidic than alkane or alkene hydrogens, but less acidic than hydroxyl hydrogens. Okay, so here's the electron paramagnetic map. The major location of the negative charge is on the carbonyl oxygen. Okay, the electron withdrawing inductive effects of the adjacent carbonyl group weakens that CH bond. The negative charge on the enolate anion is delocalized by resonance relative to the anion from the alkane or alkene. Okay, so if we were to remove one of these alpha hydrogens, this anion, what we call an enolate anion, is resonance stabilized. The negative charge can be spread between the carbon and the oxygen. Okay, so here's a table of relative acidities. Okay, I'm going to start down here at the bottom. Okay, remember each one of these is a power of 10. So alkanes and alkenes, 40 to 50. Terminal alkynes will be about 25. Alpha hydrogens on an ester about 22, and then aldehydes and ketones about 20. So you can see what we said on the earlier slides. These alpha hydrogens are more acidic than these other CH bonds. Okay, they are less acidic than alcohols, waters, carboxylic acids, and so on. Okay, if we have two carbonyls that are beta to each other, 1,3 to each other, okay, then you have more resonance structures once the anion is formed. And you can see there's a considerable drop here in pKa, considerable increase in acidity. Okay, so here's a beta diester. Here's a beta ketoester. And then up at the top, we have beta diketone, which is about 9.5. Okay, that is actually comparable to a phenol as far as acidity. Right, enolate anions can be formed either quantitatively or under equilibrium conditions. Okay, if we use a base that is stronger than the enolate anion, that results in quantitative removal of the alpha hydrogen. In other words, this goes all the way to product. Okay, an example would be sodium amide, and that would pull off an alpha hydrogen, and the pKa of the alpha hydrogens on the ketone is about 20, while the pKa of ammonia is 38. Okay, so this is definitely a weaker acid. Okay, if we were to use sodium hydroxide, then it would be an example of under equilibrium conditions. Okay, in other words, you still have a lot of starting material left. Okay, if we have a beta diketone like this, okay, the pKa of these hydrogens is about 9. And so sodium hydroxide does take this all the way to product. The enolate is resonance stabilized over both oxygens. That forms water, which is 15.7, and that's a weaker acid, okay, by several powers of 10. So this does go all the way to product. So that's an example of a quantitative formation of enolate anions. Okay, one of the things we can do with enolate anions is they are useful as nucleophiles in carbonyl addition reactions. Okay, the first example is an addition reaction. Okay, we form the enolate anion. It attacks the carbonyl carbon of a ketone, or this could be an aldehyde. And then we form this tetrahedral intermediate. And this can either undergo protonation to the alcohol or dehydration to the alkene. Okay, if our carbonyl compound is an ester, okay, then it's a little bit different. Esters, instead of undergoing addition, they will undergo substitution. Okay, so the enolate anion attacks the carbonyl of the ester. If we were to protonate this oxygen at this point, that would give us a hemiacetal. Okay, back in our chapter on aldehydes and ketones, we talked about how most hemiacetals are not stable. Okay, so it doesn't stop there. Instead, what happens is this tetrahedral intermediate collapses, oxygen pushes down, and it kicks out OR minus. And that gives us a beta ketoester. Okay, we saw something similar in the difference between the reaction of ketones versus esters in terms of Grignard reagents. Grignard reagents will undergo an addition reaction, forming a new carbon-carbon bond. Esters will add 2 equivalents of Grignard, and the second reaction is actually a substitution. Okay, so this is what's called an aldol reaction. Aldol is a contraction of the words aldehyde and alcohol. And if we take ethanal or acetaldehyde, two equivalents, and we add sodium hydroxide, we get this addition product, 3-hydroxybutanal. Okay, butanal, 4 carbons. Aldehyde takes precedence over the alcohol. Aldol originally referred to a reaction such as the first one. Today it also includes reactions of ketones. Okay, so this second reaction, even though it doesn't involve an aldehyde, is also considered an aldol reaction. Okay, so we end up with a beta hydroxy ketone. Okay, so this is 4-hydroxy 4-methyl 2-pentanone. Again, the ketone takes precedence over the alcohol in naming. Okay, so there's 3 steps in this mechanism. The first is formation of the enolate anion. And this is one of those examples of an equilibrium situation. Okay, notice based on the equilibrium arrows that this favors the starting material. Okay, so there's only a little bit of this enolate anion that's formed. Okay, but when it is formed, okay, what will happen is that it will attack a carbonyl to form a new covalent bond. And then the third step is protonation of the oxidant to give an alcohol. Okay, and these PowerPoint slides are mixed up. This should actually be the second step. Okay, so our final product is this aldol. Right, aldol products are very easily dehydrated to an alpha beta unsaturated aldehyde or ketone. Okay, so if we dehydrate, we remove a hydrogen from the alpha carbon and a OH from the beta carbon, and we get this alpha beta unsaturated aldehyde. Okay, the reason this is favorable is this alkene is now conjugated with the carbonyl group, and there's delocalization of electrons, which is favorable. All right, aldol reactions are reversible, and often little aldol product is present at equilibrium. However, equilibrium constants for the dehydration are generally large. Okay, so let me back up a minute. Okay, so these reactions are all reversible. There's little of this aldol product formed at equilibrium, but once it's dehydrated, that step is favorable. Okay, so that equilibrium constant is large. Okay, if reaction conditions bring about dehydration, good yields of an aldol product can be obtained. Okay, so those are examples with the acetaldehyde and the acetone. Those are examples of regular aldol condensations. Next, we're going to look at what are called crossed aldol condensations, where we have 2 different aldehydes or ketones. Okay, and this only works if one of the carbonyl compounds does not have alpha hydrogens. Okay, if they both have alpha hydrogens, you'll get all possible products. Okay, but here's an example of something that cannot form an enolate, and that's formaldehyde. Okay, so we form the enolate. You can have reaction of two acetone molecules with each other to form the product that we saw earlier. But there's a couple of ways to favor this crossed aldol, where the enolate attacks the formaldehyde instead of the acetone. Okay, one is that you can add the acetone slowly so that the concentration of formaldehyde is high. The second is formaldehyde is more reactive. It's less sterically hindered. Aldehydes in general are more reactive than ketones, and so this reaction with the enolate and the formaldehyde is faster than with the enolate and the acetone. Okay, these are some other good candidates for crossed aldol. Okay, none of these have an alpha hydrogen. Okay, we saw formaldehyde. Benzaldehyde would work. There's no alpha hydrogen here. There's furfural. Again, no hydrogen here. And then 2,2-dimethyl propanal. Okay, there's a tert-butyl group here, so there's no alpha hydrogen. Okay, the aldehyde hydrogen is not acidic at all. Okay, we can also do what are called intramolecular aldols. Okay, these occur when we have two carbonyls on the same compound. And this type of aldol reaction is particularly useful for the formation of 5- and 6-membered rings. Okay, because 5- and 6-membered rings are the most stable rings, they form in preference to 4 and 7 or larger rings. Okay, so let's consider this reaction. Okay, so we have alpha hydrogens here, and we have alpha hydrogens here. Okay, so if we removed an alpha hydrogen and it came around and attacked this carbonyl, that would give us a 1, 2, 3, 4, 5, 6, 7-membered ring. And if we remove one of these alpha hydrogens, that would give us a 1, 2, 3, 4, 5-membered ring. Okay, so this one's going to form and not the 7-membered ring. Okay, which is what this slide shows. Okay, so we'll remove this alpha hydrogen. It will attack this ketone carbonyl over here, form the ring, and then then we can dehydrate it to the alpha beta unsaturated ketone. Okay, the 7-membered ring does not form. All right, the difference between an aldol and a Claisen condensation is that a Claisen condensation involves an ester. Okay, so here we have two equivalents of an ester. This is ethyl ethanoate. And here we need to use a non-aqueous base. Okay, sodium ethoxide. Okay, we want this base to match our ether group on the ester. Okay, and our product will be a beta ketoester and ethanol. Okay, so this is similar. This is ethyl propanoate rather than ethyl acetate. We use 2 equivalents, and we'll add this propanoyl group to the alpha position right here. We are forming a new chiral center, so this will be racemic. Okay, we have to use ethoxide rather than hydroxide because point number 2, an aqueous base such as hydroxide would bring about hydrolysis of the ester group. Okay, so this would split into a carboxylic acid and an alcohol. Most common non-aqueous bases are sodium ethoxide in ethanol and sodium methoxide in methanol. Okay, so here's how that works. Ester alpha hydrogens are a little bit less acidic than ketone alpha hydrogens. Ketone alpha hydrogens would be about pKa 20, whereas the ester is about 22. Okay, so this is going to remove the alpha hydrogen. It's an equilibrium. Okay, it does not favor the products. We get this resonance stabilized enolate anion. This anion then attacks another unionized ester. Okay, we go through this tetrahedral intermediate. TCAI stands for tetrahedral carbonyl addition intermediate. Okay, and then that intermediate collapses when you have an ester. Right, so oxygen pushes down, kicks out ethoxide, and we get this beta ketoester. Okay, and then when we form this beta ketoester, there's one more step, and that is we have produced this compound in which the hydrogens between the 2 carbonyls are now more acidic. They're about 10.7. So this last reaction where the ethoxide, which is present at the beginning and also produced in this step, okay, that's going to remove this hydrogen. And this one is favorable because you're producing a weaker acid, namely ethanol. Okay, and then for the second step, we add dilute acid, or for the 5th step, sorry. Okay, and then we get our final product. Okay, so none of these steps have a favorable equilibrium until we get to step 4. Okay, the Dieckmann condensation, okay, that's like the aldol cyclization, but it involves esters. And just like with the aldol cyclization, this works best when we produce a 5 or a 6-membered ring. Okay, so here we have this diester, and we have alpha hydrogens here on number 5. We have alpha hydrogens on 2, which are equivalent. Okay, so if we form the anion and it attacks the more remote carbonyl, that would give us a 1, 2, 3, 4, 5-membered ring. Okay, so that would attack, push a pair of electrons up onto the oxygen. That electron pushes back down, kicks out the ethoxide, and we get this beta ketoester. Okay, and this is identical to the Claisen condensation that we saw earlier. It's just forming a cyclic compound. Okay, just like with crossed aldol condensations, we can do cross-Claisen condensations. That is a condensation between two different esters. But just like the aldol condensation that's crossed, this only works if we have an appreciable difference in reactivity, or if one of the esters has no alpha hydrogens. Okay, so these are some good candidates. Ethyl formate. This has no alpha hydrogens because there's no alpha carbon here. Diethyl carbonate also works. Diethyl oxalate or ethyl benzoate. Okay, there's no alpha hydrogen here. Okay, so these could be used as one of the esters in a cross Claisen. Okay, so this is usually carried out using an excess of the ester with no alpha hydrogens. Okay, and in the laboratory, what we often do is we'll add the ester that does have the alpha hydrogens. We'll add that very slowly to the reaction mixture that already contains the ester without the alpha hydrogens. Okay, so we form the enolate anion. It's going to attack the carbonyl. It will kick out the methoxide, and then we'll get this beta ketoester. Okay, from previous chapters, we know that base-promoted hydrolysis or saponification of an ester followed by acidification converts an ester to a carboxylic acid, okay, the byproduct being an alcohol. Beta ketoacids and beta dicarboxylic acids readily undergo decarboxylation on mild heating. Okay, so what is decarboxylation? Okay, that is loss of carbon dioxide. Okay, so here we have formation of a beta ketoester. We formed a new carbon-carbon bond. And if we hydrolyze the ester, okay, under basic conditions, we would get the carboxylate, okay, O-, but then if we add strong acid, we get the carboxylic acid. And then if we heat this, okay, we'll cleave this bond. We're going to eliminate carbon dioxide. Okay, this only happens easily if the ketone group is beta to the carboxylic acid. Okay, if it's farther on down, then it's not easily decarboxylated. Okay, so that's a beta ketoester. All right. Okay, so the result of a Claisen condensation, saponification, acidification, and decarboxylation is a ketone. Okay, so show how to bring about this conversion. Okay, so we'll first determine where a carboxylic acid group might have been. Okay, where it might have been lost. Okay, so we would have a carboxylic acid group beta to our carbonyl. Okay, so carbonyl condensations are used in the biological world for making new carbon-carbon bonds. Okay, such as the biosynthesis of fatty acids, steroids, including cholesterol, steroid hormones, and bile acids. Okay, this is the source of these biological molecules. They're built up 2 carbons at a time using acetyl coenzyme A. Okay, and that's why most fatty acids contain an even number of carbons. Okay, so we do an enzyme catalyzed Claisen condensation of 2 of these acetyl coenzyme A's. Okay, that gives you the acetoacetyl coenzyme A. And an aldol reaction with a 3rd molecule of acetyl coenzyme A is stereoselective and gives only the S enantiomer. The S enantiomer of 3-hydroxy-3-methylglutarol coenzyme A is then transformed into R-mevalonate. Okay, and this is a key intermediate in the formation of isopentyl pyrophosphate. Okay, so mevalonate is formed by the reduction of the thioester. Okay, this is an ester, except we have a sulfur instead of an oxygen here. All right, the active form of statin drugs contains a 3,5-dihydroxycarboxylate anion. Notice the similarity in structure of mevalonate to this carboxylate anion. Okay, here's a term we looked at previously, lactone. Okay, so that's a lactone is a cyclic ester. And when this hydrolyzes, the ester splits, we get an alcohol and a carboxylate. Right, the Michael reaction is the addition of an enolate anion or other nucleophile to an alpha beta unsaturated carbonyl compound. Okay, so this is one called methyl vinyl ketone, methyl group. This is a vinyl group. And here we have a beta diester. And notice that the anion does not add to the carbonyl, but instead it adds to the beta position of the alkene. Okay, and then here's a beta ketoester, and it also adds to the beta position of the alkene. Okay, if we look at the resonance forms of an alpha beta unsaturated ketone, we see that not only is the carbonyl carbon positively charged, but also the beta carbon. Okay, so because of its partial positive charge, the beta position is subject to attack by nucleophiles. Okay, so these are some combinations of reagents for effective Michael reactions. Okay, so we've got these alpha beta unsaturated compounds. And then these are good nucleophiles for use in Michael additions. Michael additions is where it adds to the beta position. Okay, these first three involve anions in which the negative charge is spread out by resonance. Amines also are good nucleophiles for Michael additions. Okay, things like Grignard reagents, which are really strong nucleophiles, will prefer to attack the carbonyl. Okay, so step one, we take a hydrogen away with a base to form the nucleophile. The nucleophile then attacks the beta position. At this point, the oxygen doesn't get protonated because, again, like aldols, most enols are unstable. Okay, an enol is where you have an alcohol directly attached to an alkene. So instead, oxygen pushes back down, and this double bond then pushes a pair of electrons onto the alpha carbon. Okay, and even if we do protonate the oxygen, then this will tautomerize to the ketone. Okay, so this is a Michael addition, and this first product involves a beta ketoester. Okay, we have to split the ester into the carboxylic acid and alcohol before we can decarboxylate it. Okay, so the base will hydrolyze this, and then adding strong acid will then protonate the carboxylic acid, okay, which will give us this. Okay, if we heat this, we'll lose carbon dioxide, and we get this 2,6-heptane diode. Okay, so here are some examples of addition of amines to alpha beta unsaturated esters. Methylamine, which is a primary amine, could actually undergo a double Michael addition. Okay, I'm gonna skip through here. Okay, and then we're going to go ahead and stop there. Okay, and I will see you on Friday. Okay, there is a sapling assignment for spectroscopy. Right now, that is that's no points. Okay, so no credit, no penalty for that assignment. Okay, that was posted specifically for one of the students that's actually taking a different lab. Okay, so I will see you on Friday.